because whatever information you you have locally, say if you do some perturbation locally, uh, it transmits that it transmits that information at the speed of sound. Okay, so for example, let me go to the notepad. For example, if you have a sphere for instance, and you throw the sphere in this direction. Okay, now of course when you're throwing it at speeds which are much lesser than speed of sound. So maybe you're throwing at what, 50 meters per second, let's say, which is also very high. 50 meters per second is close to 180 kilometers per hour. Let's say you're throwing it at this speed, which is improbable, but let's say you're doing that. So what's basically happening is the fluid here, or wherever, so fluid here, the moment you throw it, it knows that something is coming in its direction. So what it will do is it will start making way for this to pass through. Okay, so, and the information that this is travels at the speed of. Yeah, any questions? Yes. If no, nothing. Okay, so this idea is important. If you have any doubts, please raise questions. So the information that this body is actually traveling at a certain speed is radiated out at the speed of sound. Okay, so even much before this body is actually here, the fluid here actually knows that something is coming. Okay, and for incompressible flow, we approximate that the speed of sound is kind of infinite. Okay, so it's the moment you do something, everywhere in the flow field, you know that something has happened at infinite speed. Okay, so that's the basic premise of incompressible flows, which becomes slightly philosophically difficult to explain. Okay, but yeah, I could not get you, Hemang.
Yes, I was asking if the body itself is moving, wouldn't the, I mean, if speed of sound is also being generated because of the body's motion, then wouldn't Doppler's effect come into picture?
Yes, sure. That would come into picture. So it might move at c plus v. Okay, so if that's your point, perfect. I have no problems, right? Okay. So, but the idea is when your speeds are low, your fluid around know prior to its crossing that something is coming. Okay, so it is already knowing that. But for instance, you have a missile which is traveling at Mach greater than 1, then things are completely different.
Then it
So
will reach faster than the speed of sound accompanying.
yeah, speed of sound. So even the adjacent fluid actually does not know what's coming. Okay, and that creates a problem. That is the basic idea of generation of this shock waves that you see. Okay, have you heard of the shock waves? Shock waves are generated everywhere. So for example, if there is a strong explosion, all right, so you have a strong explosion somewhere, so this you okay, so initial part of the what happens is the speed of is much higher. It's actually supersonic. All right, much farther when it's weaker, then it the 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 speed of the wave then becomes, it actually something like this. The speed of the wave, pressure wave, and with distance. So it is, if this is 1, it is much higher than 1, and then it actually moves towards 1. Okay. So as it gets weaker and weaker, it moves towards the speed of sound. But initially the speed is much more than 1. Okay, that's the basic property of a shock wave. So whenever you have something that is moving faster than 1, Mach 1, you will have shock wave because of this very effect that the fluid does not have that information that things are approaching it. And the moment it approaches, there is sudden change of properties across. Okay, so it has to adjust itself, and it does by creating shock waves. So it's basically information propagation and not having enough information to adjust itself for the oncoming body. That necessitates the creation of shock waves. All right, so that's why the speed of sound is so important, and we'll try to estimate the speed of sound in right at the onset of our study. Okay, so let's see. So what is given here, what we consider is, there is a planar wave. Okay, planar wave, very weak in nature. A compression wave is traveling to the left. If you see from let's say the ground. Okay, this is a planar wave traveling. Now I change my reference frame, and I consider a very uh, small control volume in the x extent such that it covers this wave. So I cover this, and this extent doesn't matter. How much is this doesn't matter. Let's say this is of area A, extending unit depth in the plane of the screen. Okay. Now the moment I'm traveling with the wave, so I would see that there is, of course, there is oncoming velocity at the opposite, because this was traveling at c. Now since I'm traveling with the wave, I'll see that there is oncoming flow at c, and on the other side, on the side where it's downstream, my changes of properties are t plus delta p, t plus delta t, rho plus delta rho, and of course this wave was dragging this fluid um, with some velocity du. Okay, so now you would see this, the outlet of the velocity will be c minus du. Hopefully this is clear, because it's all relative. Related to this wave now, there is an outgoing velocity c minus du, and there is an incoming velocity as at c. Okay, it's basically change of reference frame. So any queries, please let me know. Okay, now what we do is
Sir,
we
what
apply.
does du signify again?
Du signifies. Okay, let me clean up my system here. As the wave passes, okay, if you, so for example, you are looking from the ground reference frame. As the wave passes, you feel that it has a tendency of dragging the fluid that it has passed through. Okay, so this dragging velocity is the du. Okay, so it's as if you're standing here and seeing the wave pass through, you will feel that the, the, the all the fluid here comes and hits you at some velocity du. Okay, so it's as if the wave, when it crosses, it drags the fluid along a little bit, and you will feel that flow on your face. Okay, whenever there is a blast wave, I think you must have felt it during your Diwali and things like that, when you have firecrackers. So there is a blast, small blast. Okay, so you feel that there's a wave coming to your face. Okay, after the blast has propagated. Okay, it's something exactly similar. Hopefully clear, right? Now, as I said, we'll apply continuity on this control volume. So if you apply the continuity, rho c is the velocity multiplied by a. Rho c a is a momentum, and this side also is a, because that's why the a cancels out. But anyways, on the outlet, you have rho plus d rho. Remember the property rho plus d rho, c minus du, that's the velocity, multiplied by a. So a cancels out, and that's why we have written like this. And there is rho c which can be subtracted out, and you are left with
So
d rho
shouldn't
by
it
rho.
be rho dv then
Rho dv. No,
for
tell me again.
momentum?
No, not momentum. This is continuity. Continuity. So
Okay,
m
okay,
dot
okay.
out, m dot out is equal to m dot in. Okay, the other way around. So rho c is m dot in, and this is m dot out. Okay. Now rearranging that, you could write d rho by rho is equal to du by c. Okay. And there are some significances where when you are increasing in velocity, you're uh, increasing in velocity, which is this. If du is in the proper direction, that means there is an increase of rho. So if here, of course, u travels in this way and increases, that means there is a substantial increase of d rho proportional to du. Okay, but the sign of du, remember, it's kind of negative here. Okay, we have not considered du here. Otherwise, you would have a negative sign in this. All right. Now applying momentum equation, what do you have? What are the forces? Pa in the positive direction, of course, right? This is area A, and then you have a negative direction P plus dP, acting on the same area again. So these are the forces. That's all. Now this will be balanced by the momentum. So momentum m dot v. So v out minus v in. What is v in? And your velocity in is c. Now after doing whole maths, so PA will be cancelled with PA here. You are left with the minus of dPA and all that math. So you are left, finally will be left with dP is equal to rho c du. All right. Okay. Now, can I substitute du by c here and get this? Okay. So what will be du by c? Du by c is going to be no, sorry. So I need to substitute c du. C du would be c square by rho d rho. Agree?
Yes, from the above equation.
Yes. So if I substitute this here, so I should be able to get this. Okay. So dP is equal to c square. So you get a very important equation where dP d rho is c square from from arguments of momentum only. Okay. So this is from the right from just from the momentum equations we are able to get this. Now we appeal to thermodynamics a little bit because things are changing. Pressure is changing, temperature is changing, density is changing. So we can appeal to the thermodynamic process of this compression wave. So what we are saying is this compression wave travels at a speed c, and this compression, as the wave is crossing the uncompressed regions, it's compressing in a mechanism which is adiabatic. Okay. So why adiabatic? Because speed of this is fast enough to prevent any heat transfer to take place. All right. So the time scales of this of the passing of the wave is much smaller than the time scale of any effective heat transfer that can take place due to the rise in temperature. Okay. So that's the basic assumption. And if you do that, then of course the whole process becomes adiabatic, and you're not considering any losses as such. So it becomes isentropic. Hopefully you're acquainted with this process as isentropic. Okay. Now what is an isentropic process? How do you write an isentropic process? P is equal to some constant rho to the power gamma. Right? Do you write it as like this? Yes or no? Yes, or I'm wrong. Okay. So what is an adiabatic process? PV to the power gamma is some constant. Okay. Now, if V is specific volume has relation to density as 1 by rho. Okay, so you could write it as P by rho to the power gamma is some constant, and that's what I have written here. Okay. Now, if I want to construct what's my PP d rho K gamma gamma minus 1. Okay, so K, okay, gamma K, if I rho gamma, okay, so what I can do is I can write it as rho. I'm just rearranging stuff. That's it. Okay, this can then be written as the pressure itself. So what you end up with, you have a gamma P by rho. So, so your dP d rho at constant entropy becomes gamma P by rho. And for a gas, we use the equation of state. P by rho is nothing but RT. So if I substitute that now, so gamma RT becomes your dP d rho, and dP d rho, as we saw from the momentum equation, is the square of the speed of the wave. So this is nothing but the square of the speed of wave. So we got a very interesting relation of the speed of sound, which is gamma r. Okay, so
So how do you know that it is isentropic?
how do I know? Uh, it's it's basically an assumption. So we don't know a priori. Okay, we don't know a priori, but experimentally it has been found that the time scale of this passing of the wave does not allow effective heat transfer to take place at all. So basically, this pressurizing process is basically adiabatic. Okay, and experimentally it has been shown to be adiabatic at all, and most of the atmospheric conditions, sound wave is adiabatic.
No, but if it is adiabatic, then for it to be isentropic also, it has to be reversible.
Reversible, yes, but yes.
Then how is
So
that satisfied?
it's a good question. Reversible only if it is a very weak wave. Okay, if it is strong shock wave, then of course it is not reversible at all. Okay, so only for a weak wave, we can say that okay, my things are such that there has not been much losses that has been induced by the weak wave.
But then how do you put the bounds, whether it is weak or strong? How do you define that?
Weak or strong, the change of pressure dP or the change of density, they are infinitesimal. Okay, so that's the definition of something very weak. If there is a huge change of pressure across the wave, then of course the wave is not weak at all. Okay, infinitesimal
Fine.
I would mean it's dP by P could be order of 10 to the power minus 6 or so. Okay, so something like that.
Okay.
All right, clear, right?
Yes, sir.
Okay, all right. This part, criterion for neglect of compressible effects is what we'll skip for the time being, and we'll come to it when we will naturally come to it slightly later. Okay. So now these are some useful thermodynamic relations. Hopefully you are aware of all of them. Equation of state is what we just used. Basically, the way of writing this is more appropriately is dE is CVdT and dH this is internal energy, and this is enthalpy, of course, CPdT. Okay, and specific heats of constant pressure, constant volume are these. Cp minus Cv is, of course, the gas constant, and speed of sound, we saw this, and change of entropy is given by this. So, are you aware of this too?
Yes. Yeah.
Yes.
Yes. Okay, good. Okay, so, but let me ask you. So, how do you go about deriving this? Take one of them. Let's say the first one. Can I derive this? Yes. So your first law states that TdS is equal to dH minus of VdP. Do you agree?
Yes.
Yes. So now this, if everything is specific, this specific volume, so I can write it as 1 by rho. Right. So now I could substitute dH as Cp dt, and then we have dP, and rho can be substituted as from the state equation as P by RT. So RT goes on the top. We have this ds. I'm sorry. So ds becomes Cp dt by T minus R dP by T. Now you integrate from one state to another. So first state to the second state, then it becomes Cp ln T2 by T1 minus R ln T2 by T1. Okay. And similarly, you consider TdS as dE plus PdV in this case. Okay, and then integrate, you should be able to get this. All right. And as discussed, this is the condition for any adiabatic process from process 1 to process 2. If it's adiabatic, you can have the pressure density relations like this, temperature relations like this. So these are pretty straightforward. You should be able to, you should know this, because most of our flows will consider an approximation where things are adiabatic, as well as there are no friction losses and other kind of losses. So if there are no friction losses, you could effectively say they are quasi flows, and you can approximate them by isentropic processes. Okay. All right. So this is the part where we look at this, I think, and then I can take some questions, and then we can move forward a little bit further. Then. Okay. All right. So what is a 1D flow? What is a 1D flow? We have okay, but I need a slightly more technical definition.
The change of all of the properties can happen only in one direction along one axis.
Hmm. Okay, this sounds better. This sounds better. So basically, your velocity vector, okay, just one variable, okay, space x or y or z, then this velocity vector, this flow field is one dimensional. Okay. For example, remember the pipe problem. You had the pipe, and I had this parabolic profile, if you remember. So we derived u by u max was was 1 minus r by r square. Capital R, capital is the radius of the pipe. Here, u, u max is constant. U is just a variable of r. So, of course, it's a 1D flow. Realize that. Okay. So, whenever you're seeing a flow or studying a flow, ask questions like this: 1D, 2D, 3D, what it is. All right. So, pipe flow is an example of 1D flow. Channel feature y by h 1D flows. Here, also the situation is similar, but slightly different in the sense that at a particular section 1, if you look at this channel where there is a 1D flow, we'll assume that across the full channel the velocity is uniform, but it is only varying in the streamwise direction as it is moving. Okay, so basically u is a function of x, nothing else, because it is not changing with y. As against, you remember in a pipe, it was changing with y, but it was not changing in x. So here, situation is slightly reversed, but still it is 1D, of course, because of this definition. And the assumptions are okay: 1D, frictionless invisible, and there is no heat. Of course, there could be heat input, but in this analysis, what we are going to do, um, we are considering this to be 0. So that way it's adiabatic, and there are no losses. So basically becomes isentropic, and your isentropic relations become between the state variables like pressure, density, and temperature. Your isentropic relation is valid. Okay. Now consider a flow like this, where you have a certain change of the area, and there is an oncoming with pressure P, U, and at an area A, and it is the outgoing is at pressure P plus dP, U plus U, A plus dA, and you take a control volume which is shown in the dotted line. Okay, so this is the control volume, and the area on the sides are given as dA sides, which also will come. Okay, apply continuity. What you have is rho U A is equal to constant. Okay. Now, if rho U is equal to constant, that is the same as rho plus d rho, that is going out, you add velocity u plus du, add velocity a plus dA. So if you rearrange stuff and of course you see that this rho ua cancels out with all the rest of the things, and then divide by the same constant rho ua, you're going to end up like this. I hope you see it immediately. Rho ua is, you take a differential, it you can actually express the whole thing as d rho by rho plus du by u plus dA by a is equal to 0. Right. So this is the continuity equation for a 1D steady flow. 1D steady flow. All right. Any doubts? Please let me know. We can derive it fully also. I can go to the notepad, do the derivation. No problems. Okay. Should I?
No problem. It's fine.
Hopefully it's okay.
Yes, it's quite apparent.
Oh yeah, good. Okay. Now, for everybody else also, right? Anybody don't feel
Yes.
don't have to feel shy. Okay, so you can be very upfront. Anyways, you guys are very upfront, so you should be very upfront. All right. So direction, which is having a magnitude of PA, so plus PA of course, and there is on the right it's acting in this negative direction, so P plus dP acting over A plus dA, so that's what is written here. But then there is this on this dA portion, since it is this extent is taken to be very small, let's say delta x, which is tending to 0, let's say. So what you could do is I could take an average pressure across this, which is the average of the left and the average taken over the left and the right pressures. So basically P plus dP by 2. Okay, so that's P plus dP by 2, and it is acting over this area dA. Okay, so it's imagine it's we did that this kind of analysis somewhere else also, if I remember right, in deriving the continuity from the control volume analysis. So it's exactly similar idea, where dA is the difference of the pressure. So imagine this to be a trapezoidal, not trapezoid. I mean it's a section, it's a frustum kind of cone. All right. So frustum is basically a chopped up cone, right? It looks like a projected trapezoid. Projected, it will look like a trapezoid. So imagine something like this, and this is the dA area. Okay, and this P plus dP is acting normally on this, and so basically if you project it on this direction, so this as well as this, because it's the same, so this will be, because A is already this, A plus dA will give you the projected area, which is D plus A plus dA. So now P plus dP multiplied by this projected area will be the force that is acting in the positive direction, along this direction. Okay, so dA is the projected area of this. It's not the actual area, but the projected. Now sum up all the things. And what m dot V out minus V in, that's the momentum flux, and there is no unsteady terms, of course, so that's why these terms are the only which survives. So m dot is rho UA, and rho UA across one section, on the left section it will be same as on the right, so you can keep it as rho UA, and then this is U plus du is a V out, and V in is U. So when you do this, U cancels out, and you are left with dP is equal to minus of rho U du.
Sir, if the flow be compressible, then we haven't captured the idea of stresses which can generate, maybe tensile or compressive.
So tensile or compressive stresses will be governed by, of course, we assumed inviscid. So any viscous forces that can be there is not included in this analysis. All right.
How are tensile forces viscous?
Tensile forces can be viscous. Every forces. So if you remember, sigma, or what I how x how x is mu.
Okay.
All right. So already had discussed viscosity for it to generate this. Okay. Now, of course, we saw this dP d rho is c square, and dP is equal to c square d rho. So if I use this on this, I should be able to get a relation between d rho and du. Hopefully, you are able to see this. So dP I get as minus of rho u du, and also dP from thermodynamics and the speed of sound wave is d rho, right? So if I if I substitute it here, so c square d rho is nothing but minus of rho u du, and then if I take the c square this way, so d rho by rho is minus of u square by c square du by u. Okay, now this u square by c square
Is the Mach number.
is Mach square. Okay, because the definition of Mach is this u by c. That's the definition of Mach,
Okay.
Mach number. Mach number is a very important number in compressible flows. I think the most important number, I would say. Okay, and when you have viscous effects, when you consider viscous effects, of course Reynolds number also becomes an important parameter. But first cut design, Mach number is the most important. So you see d rho by rho is minus of m square du by u. Okay, now let's look at let's look at this in a bit of detail. Okay. D rho by rho minus of m square du by u. All right. Now, what is the limit of the Mach number for which we say things can be incompressible and we don't care about any changes in density? Okay, so it's an empirical number where it's conventionally decided. Okay, if my density change d rho by rho is less than 10%, I would say my incompressible flow will capture it pretty well. So I can very well say that my rho is constant everywhere. Okay. Basically, it comes to this. So almost like about 10% or so. So it's the value of is 0.1. So what is the equivalent du by u that you need in terms of Mach number? Uh, is what you have to what you can determine from here. Okay, so if you're oh no, I kind of goofed up a little bit. So 10% with respect to the change of du by u. Okay, so that's the basic argument. So basically, your m square, if your m square is close to 0.1, then you say that okay, my change in percentage change in density is 10% of the percentage change of du, and I would then be compelled to include the compressibility effects. If it is less than that, I will not. Okay. So this is my borderline case. M square is equal to 0.1. So M turns out to be something like 0.3ish. Okay. So if your Mach number is below 0.3, I would say that things are pretty much incompressible. But this is not black and white, but it's a gray region, of course. But Mach greater than 0.3, I will start incorporating compressibility effects. Okay, so let's get an estimate of what's 0.3 in case of air. So at T at about 300 Kelvin, which is the normal room temperature, let's say, or I don't know if you want a global thing, so it may be 288, 15 degrees Celsius maybe, whatever. So the C turns out to be in those scenarios 340 meters per second. That's the speed of sound. 3 of that is something like 100 meters per second. 0.3 C. Sorry, C. Can I say very close? 100 meters per second. So 100 meters per second is how fast is 100 meters per second? 100 meters per second is something like 360 kilometers per hour. Would you say? Am I right here? 3.6, right? Yeah. 360 kilometers per hour. 360 kilometers per hour. I don't think even the top speed in your F1 races reaches 360. Does it reach 360? Those who are F1 enthusiasts here, I think 330, 340, or 310, something like that. So even the fastest of cars or and fastest of sports that we have till today will not actually cross this incompressibility boundary. Okay, so that's it shows you the domain of the surrounding that we live in. It's pretty much incompressible, and that's why the intuition that we develop also for fluid flows is incompressible intuition. So we'll see that when you go to the other domain, things are actually very counterintuitive that way. So hopefully this is clear. I mean the kind of domains, speed domains we are looking at is much higher speeds. For example, now if you go to a bullet train, I don't know, bullet train can reach 500 kilometer per hour, something like that. So here you might have to take into compressibility effects, but that also will be very minor. Okay, so that also is very minor. Okay, so that was the context of your m equal to 0.3 being a cutoff for incorporating compressibility effects. If you have more than mark equal to 0.3, you are supposed to do that, incorporate compressibility. Okay, so we go to our here, d rho by rho is equal to minus of m square du by u, and we substitute this back to our continuity equation here. Okay, so d rho by rho plus du by u plus dA by A is equal to 0, and d rho by rho can be written as minus of m square du by u. Okay, once you do that, you end up this. So this is area, this is called speed relation. Thinking about designing a model that will take you to from subsonic to supersonic speed. You want to reach supersonic speed to be able to get higher and higher thrust. I mentioned that, right? Okay. So yes, so model design. This is the gist of the whole thing that we did, and now let's discuss this relation a little bit. Okay, so let's go to minus m squared du by u okay. Now I want to increase my velocity and my m is subsonic, less than 1. So this relation tells you that your dA has to be less than 0. So dA has to decrease, right? Am I right? M is less than 1. This is positive and this is positive. No. There is a negative sign. Did I miss? Okay. So your dA has to be less than 0, which makes sense because if your mark is less than 1, we see that you need to have a converging section. Even in a venturi and things like that, you saw that there is a velocity increase as you converge, as the geometry is converging. So your dA is negative here because the area is reducing as you move in x. All right. Whereas on the other way around, if I want the velocity to reduce for Mach subsonic, then your dA has to increase. Okay, which is also governed by this equation, if you see. So subsonic 1 minus m square is positive, but I want this to be negative, and so this has to be equivalently negative dA. So dA has to be positive to make it negative. So your things have to diverge. Okay, so to reduce your velocity, your DA has to be 12. Okay, now let's come to things when it becomes supersonic. Supersonic 1 minus m square itself is negative all the time. So now if I want to have a du greater than 0, I want to accelerate my flow. So dA dA becomes positive, okay, because this is negative, this is negative, and dA has to be positive to match the signs. So if you are already m is equal to greater than 1 and you want to increase your velocity even further, so you see you have to increase your area. If you increase your area, you're going to actually speed up when you are supersonic. Okay, so du greater than 0. Whereas on the other hand, if you want to decrease your speeds, that is du is less than 0, then your dA according to this should be should be should also be less than 0. If you have a converging section, right, and your Mach number is greater than 1 already, then you are actually reducing your speeds here. Okay, so u is reducing. So this and this is very counterintuitive to what we actually already know for low speeds. Okay, so the moment you go to high speeds, things have started to become very, very counterintuitive. Okay, and what do you think is the reason for this? Yes, I barely heard that. Who is this? Pranav, was it?
Sir, could you please repeat?
Last sentence is it's become very counterintuitive because you see, for when Mach was subsonic, for subsonic flows, when you had to increase the velocity, you had to actually reduce the area of cross section, which makes sense, intuitive. But for a supersonic flow, to increase the velocity, you actually have to diverge. You have to have a diverging area. All right. So when I first studied it, found it to be very uncomforting actually. So it's completely kind of dissolves your idea of intuition, things like that. Okay. So the bottom line is intuition also, however good it may be, it's always good to question your intuitions more often than not. Okay. So deepens your understanding. So intuitions are good, but you should question them also. All right. Any queries till now? I think if you have many queries, also should not surprise me. So tell me. All right, then I can move forward. So basically, the question is, why does it happen that way? So it lies in the answer lies here. Okay. So when Mach so so d rho by rho, when Mach number is greater than 1, more than the change in velocity. Okay, so the density is changing much faster than the velocity itself when the Mach number is greater than 1. Whereas when the Mach number was subsonic, the change of density was not as much. And when it is less than 0.3, even smaller, less than 10% of the change in velocity. So this is the whole game here. The change in density makes up for that. for the area. Okay, so that's why you need to have a different plan for the area for a for uh, for Mach number greater than 1 supersonic flows. So this is the key, because the area changes so density changes so drastically that you have to have a different plan for the area. So the whole thing actually becomes much completely opposite to what you generally expect in a subsonic flow. Okay, so there you get a plan for how to go to a supersonic regime from a subsonic regime. So this is the last topic that will discuss, and then that's it. So you get an idea of what your CD nozzle will look like. Okay, you start off from a stationary flow at a very high pressure. Okay, so you want to push that flow at a very high pressure through a converging nozzle where the flows is subsonic, because you're starting from Mach 0 and you're trying to accelerate. Okay, so here it's subsonic, and then when you reach Mach equal to 1, you have to keep that area to be the minimum, because m1 minus m squared du by u was minus dA by a. So when Mach reaches 1, the whole thing becomes 0 here. So the dA also has to be 0. So this dA equal to 0 part, where the area reaches the minimum. Okay, so that is called the throat. So the flow will reach Mach equal to 1 here, and later on here, slightly downstream, when it is already become supersonic, slightly supersonic, then to even accelerate further, you have to completely change the plan that you had here. So then what you need to do is to diverge such that you get a even further increase of your Mach number. So your Mach number can increase further, and then here you can keep either it could be atmospheric, or you could also drain the chamber here to very minimal vacuum pressures also. Vacuum pressures. If it is an experimental setup that you're trying to build to create supersonic flows, you can actually take out suck out air from here and make it pressure as low as possible, so that you can get maximum pressure differences to create this supersonic flow. So basically, your converging diverging section has this philosophy. Okay, so you have a converging section, and then diverging at the throat you have Mach equal to 1, and this is what is used in all your. This philosophy is used in all your nozzles. As you can see, this is one of the taken directly from the NASA website here. Okay, so initial that I showed you some rocket motor nozzle, right? You see, you can see the throat area here is visible, and then things are diverging. Diverging does not mean that it will reduce in speed, since the throat you have already reached Mach equal to 1, things will be supersonic. So that was the basic philosophy of designing of a converging diverging nozzle. Now one more interesting point is, once you reach Mach 1 here, okay, once you reach Mach 1 here, then you understand that there's Mach greater than 1 on this side, correct? So the thing is, any disturbance that you do here will not be able to propagate beyond this point, because there's a Mach 1 there sitting there. Okay, so for example, for a particular pressure here, you reach Mach 1. Now if you increase the pressure even further, all right, you will not be able to push more mass flow rate beyond this what you're already pushing when Mach equal to 1. So that's the maximum mass flow rate that this nozzle can handle. Okay, so if you want to increase your mass flow rate even further, to increase your mass flow rate dot V exit was your thrust. Now if you want to increase your thrust even further by increasing the mass flow rate, then you would have to change the design of the nozzle completely. Okay, because the mass flow rate, maximum mass flow rate is bounded because of this property. So this maximum bounded mass flow rate that you can achieve for a certain pressure, and even higher pressures won't matter at that point, is called choke flow. The flow is choked. Okay, so that's a property of converging diverging nozzle actually. So to have different mass flows at Mach equal to 1, you might have to have a variable geometry or have to have separate nozzles altogether to be able to uh, get different mass flow rates. Okay, so a lot of things to wrap your head around. Go through it. Very interesting topic, and it's the order of the day. I think more and more we should be able to master this subject to be able to build compressible systems. You see, compressible everything high tech and in the defense world is basically compressible nowadays. So it's a very important topic, and I believe there will be a much more specialized or a much more devoted elective course later on in your in your 4-year curricula here. So there will be a course on gas dynamics later on. So any queries on the philosophy of designing a CD nozzle? The philosophy is basically based on what we discussed here. It's basically based on this area velocity relation. Okay. Okay. Any more queries, please? If not, I'll stop sharing and maybe take a screenshot.